Okay, for electron configurations, like I said, one of the hardest parts is getting the right order of filling for the orbitals because there are some anomalies and they don't always fill the way you'd expect them to. Before long, hopefully, you'll be able to just look at where the element is in the periodic table and you'll be able to tell what its electron configuration is from where it is and which parts of the periodic table you have to pass by in order to get to that element. Because as it turns out, certain parts of the periodic table correspond to certain types of orbitals filling. And so if you just look at what parts you're passing by as you just take your finger and sort of go left to right across the elements until you get to the one you're looking for, you can see, okay, well, I've got to fill up these orbitals and then I have to fill these and then these and then these and so on. And you'll have your electron configuration by the time you actually get to the element you're interested in. In the meantime, though, there is an easier way to do it than just trying to memorize that orbital filling order that I just wrote. And that is to write out the orbitals in columns. So say the s orbitals, you've got an s orbital in n equals 1, and there's an s orbital in n equals 2. In fact, there's an s orbital in every shell. And for ground state electron configurations, we really don't have to be concerned about anything past 7. So I'll stop there. And then you do the same with the p and the d and the f orbitals. But you got to remember, the p orbitals don't start until the second shell. So there is no 1p orbital. So the first one is at 2p. Just make sure that you draw that right next to 2s. And then we have 3p, 4p, 5p, 6p, and 7p. Then you do the same with the d orbitals. But remember, there are no d orbitals in the first or second shell, so the d orbitals begin with 3d. Okay, then you do the same with the f orbitals. But remember, f's don't start until n equals 4. So we go 4f, 5f, 6f, 7f. And now, in order to basically determine the order of filling, all you need is to take a pen or pencil and draw diagonal lines across this figure. Okay, from basically upper right to lower left. So the first one goes like so, second one goes like that, third one goes like that, fourth one goes like that, fifth one goes like that, and so on, and so on, and so on. And if you follow the arrows, you'll get the orbitals in the correct order. And in fact, you can actually do that. We'll do that right now and compare it to the order I just wrote on the previous page. So the first one you come to would be 1s. Then you would come to 2s. Then we come to 2p and then 3s. After 3s, we come to 3p and 4s. After 4s, we come to 3d, 4p, and 5s. After that, we come to 4d, 5p, 6s, and I think that's where the other list ended. Yes, it is. So now we can compare. Oops. Let's see here. 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s. So there you go. This is actually very simple. I'm really surprised that the book doesn't seem to have this in there anywhere. It's not like it's, it's not like it's trademarked or anything. In fact, if you go online and Google something like orbital filling order or something like that, you will probably find, dozens of versions of this. set up with different graphics and different fonts and things like that. And so it might be a good idea just to do that orbital filling order, and or something like that if you don't get what you're looking for on the first try, and just save one that looks nice and makes sense to you, and consult that whenever you're doing electron configurations, because this is, or worst comes to worst, you can always reproduce it yourself. And so that's, this is a really good device for remembering what the filling order should be. When you do, there are also some shortcuts you can use in addition to what we just did, and that is the noble gas abbreviation. I pointed out on the last page that noble gas elements have entire shells that are filled. And what that means is that their electron configurations are the same as the configuration for the core electrons of other elements in the ground state. Okay, the core electrons, remember, are essentially all of the electrons in an atom except the valence electrons. And the valence electrons are the ones in the outermost shell. So the core electrons are the inner electrons. As a result of this, when you're doing electron configurations, one handy shortcut is to use the symbol of the last previous noble gas in square brackets to represent the core electrons of an element. So a good example, I mean, the simplest case where you could do that would be to look at the electron configuration of helium. Helium is the second element, it has 2 electrons. Its electron configuration is 1s2. If you look at the next element in terms of atomic number, it's lithium, which has an atomic number of 3, or 3 electrons. Its electron configuration is 1s2, 2s1. Well, notice how the inner shell has the same electron configuration as helium. So you could write that as He in brackets, followed by whatever lithium has beyond what helium has, which is 2s1. Now, of course, in this case, you didn't really save yourself very much effort by doing that. But there are future cases, with other bigger elements with more electrons, where you can actually save yourself quite a lot of work by doing that. So we can look at beryllium, which is 1s2, 2s2. That would be helium 2s2 for a configuration. There's boron, which has a configuration 1s2, 2s2, 2p1. That would be helium in brackets followed by 2s2, 2p1. Because 2s2, 2p1 is what boron has beyond what helium has. And we go on to the next noble gas, we'd skip a few here, which is neon. Neon is 1s2, 2s2, 2p6. So the first shell and the second shell are both filled. If you go on to sodium, which has atomic number 11, meaning it has one electron beyond what neon has, sodium's electron configuration would be 1s2, 2s2, 2p6, 3s1. And that would be neon in brackets, followed by 3s1. And in this case, you actually did save yourself a fair amount of effort. And so that's basically noble gas abbreviation. It's something that can save even more effort for the bigger elements. And I'll do a few examples here of noble gas abbreviations. If you want the configuration for chlorine, which has an atomic number of 17, the full electron configuration will be 1s2, 2s2, 2p6, 3s2, 3p5. Okay, out of this, first of all, you'll notice that chlorine is in group 7, and that's because in its valence shell, it has 7 electrons. Its valence shell being the shell with the highest N number, 3 in this case, and the total number of electrons in the third shell is 2 plus 5, which is 7. And that's why chlorine is in group 7A. Using a noble gas abbreviation, we look back at the last previous noble gas in terms of atomic number, and it turns out that that's way back at neon, which has an atomic number of 10, and neon's electron configuration is that right there. 1s2, 2s2, 2p6. So essentially what you're doing for most noble gas abbreviations of electron configurations is you're writing the symbol for the last previous noble gas, and then you're writing the valence shell for the element that you're dealing with. So for chlorine, that would be neon 3s2, 3p5. So that would be using the noble gas abbreviation. Let's see, another one, silicon. 14 is the atomic number. That's 1s2, 2s2, 2p6, 3s2, 3p2. Notice how there's a total of 2 plus 2 or 4 electrons in the valence shell. And silicon is in group 4A. If you look at the last previous noble gas, it is neon, which has 10 electrons and this electron configuration here. So silicon would be neon plus 3s2, 3p2. The next one is strontium, Sr, and that has an atomic number of 38. So now we're talking some work here. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and here's the first anomaly, 3d10, and then 4p6, and 5s2. All right, one thing you'll notice about strontium is that it's in group 2A. Notice it has 2 electrons in the valence shell. If you look back at the last previous noble gas, you'll see that it is krypton, which has this right here as an electron configuration. So again, the configuration of this element is just the last previous noble gas plus the valence shell. Oxygen is a really easy one. It's only got 8 electrons, 1s2, 2s2, 2p4. You'll notice the valence shell has a total of 6 electrons, and it's in group 6. That is not a coincidence. The last previous noble gas was helium, and the configuration of helium was 1s2, so you can replace that part of the configuration with He, and then replace the rest with the valence shell, 2s2, 2p4. All right, so there you go. The next part, actually, section 8.4, is where we actually get a look at the different parts of the periodic table and which parts of the electron configurations they correspond to. Okay, so electron configurations, valence electrons, and the periodic table. Some of that I tried to preview in the last section, so it won't be totally new. And it turns out that, actually, I think I mentioned this earlier today too. Mendeleev didn't know about things like atomic number or number of protons or number of electrons, but just the fact that he took and arranged the elements that were known at his time in groups with similar properties ultimately meant that he was arranging them in groups that had similar numbers of outer shell electrons. That's the way it worked out. And that's because outer shell electrons or valence electrons are actually responsible for most of the chemical properties of an element. Okay, and so that what I said is it applies to the A groups, the main groups anyway. The transition elements get a little bit more complicated, as we've actually already seen. Okay, so for the A groups, if you arrange the elements so that elements with similar properties are in vertical columns, then what you end up with ultimately is elements with the same number of valence electrons in these columns. And it's been arranged and numbered so that those elements, basically the number of the group is the number of valence electrons for the A groups. Okay. Even though the elements in any given column or group will have the same number of valence electrons for the A groups, the N number, that is the number of the outermost shell, will increase by 1 for each step down the group. And of course, as it turns out, we know that, well, we've heard before that the number of the valence shell is just the period number in the periodic table. Some periodic tables have the numbers going down the left-hand side of the periodic table and some don't, but you can always number them yourself if you want to. And so, you know, if it's an element that's in the fourth row down, then that just means that n equals 4 is the valence shell. This is important again because valence electrons are responsible for bonding. And bonding is what leads to chemical properties. Because really, when you're talking about, you know, what are chemical properties for an element, it's basically how does it behave in chemical reactions. And chemical reactions are all about bonding. And bonding is all about electrons, specifically valence electrons. So that is pretty important. And so just, valence electrons are all of the electrons with the highest value of N. That's for the A groups. Or for the B groups, that would be all of the electrons with the highest value of N and D electrons in the N-1 level. And that's for the B groups. The core electrons would be all the others. Okay, so the valence electrons, once we exclude them, everything else is a core electron. And of course, the core electrons, if you're talking about a ground state atom anyway, the core electrons will be held in principal energy levels that are complete. And that's why we can use noble gas abbreviations for the core electrons. Okay, the way that the orbital types correspond to the periodic table, as I mentioned before, is a very useful thing to know. And those are what are known as orbital blocks in the periodic table. And that's going back to what I said a moment ago. Since the number of valence electrons corresponds to the position in the table, The position also corresponds to what type of orbital is being filled when you run out of electrons, basically. Okay, so it's basically the last type of orbital to fill for a given element. You can tell what that is based on where the element is in the periodic table. So groups 1 and 2 of the A groups, those would be known as the S block. With N being the same as the period number. That is, the number that goes with the S-type orbital would be the same as the period number. Going left to right across the periodic table, you next come to the actually the other A groups, because if you're starting at the top of the periodic table, of course, there are no transition elements up there. So going across the top of the periodic table, you would next come to groups 3 through 8A, and that's known as the P block. And that means for those elements in that area of the periodic table, the last orbital to fill, or the last orbital to get any electrons in it, it won't necessarily fill up, but the last one with any electrons in it will be a p-type orbital, and it will be in the shell whose number is the same as the period. All right, then there are the transition elements. Or the B groups. That's known as the D block because D electrons would be the last ones in for those elements. And the number associated with the D block would be the period number -1. Or actually, let me put it like this, N equals N would be the period number -1. And then there are the lanthanides and actinides. Those guys are known as the F block. And the N number associated with the, say, the orbital would be the period number -2. Okay. Notice how the number of the columns in any given block is the same as the number of electrons that's possible for that type of orbital to hold. And that's because for each element left to right, as you progress through the periodic table, you're essentially adding 1 proton and 1 electron, for each step left to right. And so if the P block basically starts with 1 electron in the p orbitals of the valence shell, then you can add a second and a third and a fourth and a fifth. But once you add the 6th electron for the p orbitals in the valence shell, you've filled that shell. And if you have any more to go, then you have to go down to the next period with the s orbitals of the next shell, and so on and so on and so on. So if you notice, there are, like I said, 6 spaces in. All right, so looking at the periodic table, these first 2 groups here, these are the S block. And these groups over here are the P block. The transition elements in the middle would be the D block, and these groups down here would be the F block. Notice that for s orbitals, there's only one single s orbital in any given shell, and that can hold 2 electrons. Notice there are 2 elements in the s block for each period. For the p orbitals in any given shell that has them, you can hold 6 electrons. Notice how many elements there are in the p block. 1, 2, 3, 4, 5, 6. For the d orbitals in any given shell that has them, you can fit a total of 10 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And for the F blocks, for F orbitals in any given shell that has them, the total number of electrons you can fit into the F orbitals is 14. And if you count across from here to here, you get 14. And so essentially what you're doing is you're adding 1 more electron to that type of orbital for each step left to right. Okay, so and also the number of valence electrons is equal to the group number. That's for the A groups, with the exception of helium. Helium is put in with the noble gases because it has a completely filled shell of electrons, which gives it properties similar to the other noble gases, even though it does not have the same number of valence electrons. And there we go. Actually, we're up to 30 minutes again, so I guess I'll have to continue in the next segment.